He's just an idiot. Ignore me.
I sit here every single.
Sit there.
No, I sit here. Yeah.
All right.
Oh, wow.
Oh, imperial units, fun.
This should be where we left off.
Gosh. I hate it.
Okay, let's not, obviously over the weekend, it was very cloudy, so we're gonna have until, listen, Thursday to get it done, Thursday.
Yeah,
Did you
and
see
there
the
were a
meteor
bunch of
shower?
meteor showers too.
Perseids were going on, right? I forget what chapter it is, we talk about comets. Comets are the reason why we have meteor showers. Okay, off topic, meteor. We usually hear meteor when we talk about,
Bronx.
like, you turn on the television, your phone, you look at the weather report, and guess who talks to you?
A meteorologist.
Why are they called meteorologists? It's the same word.
They're studying meters.
Is the weather meteors?
I don't know. It's weather.
It's interesting, but that's got to be answered, right? If you want to look it up for yourself before I explain, I won't explain to you today, but that needs to be answered, right?
Because they want to be called that. And a
No.
story.
It's got a real reason. Okay, so we left off on, here's the problem. The problem is in astronomy, you deal with, pun intended or not pun intended, but we deal with astronomical distances. We can't even wrap our head around how far these distances are. So how do we measure things in astronomy? And this is kind of where we left off. One way is with imperial units, and we finally came to the conclusion. Why is this not clicking? We came to the conclusion that my clicker isn't working. No, we came to the conclusion that imperial units were those units that we use here in the United States all the time. Now, if you're a scientist, you probably use different one, but in everyday language, everyday usage, these are the type of units we use. For distances, we use inches, feet, yard, and miles. Longer than a mile is called a furlong. For weights, we use ounce, pounds. We don't use stone, and we do use ton. And lastly, for volumes or for fluid volumes, we use pints, quarts, gallons. Heck, is some you probably heard about bushels as well too. Those are all measurements that we use for how much stuff do we got type in volume. All right, what scientists, and by the way, during astronomy, because we live in the United States, we use these things. We will be occasionally using your imperial units, but most of the time we're going to be using the international standard. The international standard are the ones that you're familiar with, McKinley, the metric system. Therefore, we're going to be using. So, for instance, for astronomy, we're going to be using meters, right? Kilometers, 1,000 meters, right? Those are general what we're talking about. Yes, we have other measurements for volume and whatnot, but I'm generally going to use this. By the way, they're called SI units, even though it's spelled International Standard Units, and it's because of the French. The French put their words backward. I think Spanish does the same thing, but in French, I don't speak them. I have a French name, I speak German, but this is the international standard written, Le Système International. But they always put it backwards, as we would think of it, but they would think we put it backwards.
If you speak German, then why didn't you teach the German?
Warum?
So much.
Weil ich kann nur ein bisschen Deutsch sprechen.
What?
I said, because I can only speak little German.
Makes sense.
I can speak good conversational German.
I
would never claim that I can actually speak great German in terms of correct grammar.
Well, wouldn't you want more like someone who knows how to speak the language, like everyday stuff, instead of learning the grammar?
Maybe. So we have the international standard meters and kilometers, which works great until it doesn't work great. When is it not going to work great?
When it's like thousands and thousands.
When it's not even what we would consider far away astronomical. Tell me something that's close to us.
Flag.
No, astronomy speaking. Tell me something that's close.
Satellite.
Satellites 22,000 miles away. Unless that's geosynchronous orbit or geostationary orbit, and then low Earth orbits hundreds of miles. Like the International Space Station is about 200 miles. Right now, I don't know how many are up there right now. 6, right? Usually it's somewhere around 6. There's 6 people floating, spinning around the Earth right now. They live about 200 miles above our heads right now. And if you are interested, so it orbits the Earth once every about 90 minutes. You can look up and you can see the International Space Station. It looks like a white dot, but you can see it passing overhead. It's very bright. You can see it either right before sunrise or right after sunset. You can see it very well. It's a big white dot, and it goes very fast. About that fast across the sky. It's super fast as it crosses. Okay, the but here is, as I just said, the universe is very large, and if we start using meters or imperial units, miles, then we need a big whiteboard to write those numbers down. So just restricting ourselves to our solar system. I haven't fully defined what our solar system is yet. You got a pretty good impression of it. Early on, astronomers were like, we need a different measuring unit. And so this is the first one you're probably not familiar with. We'll write it down here in a second. It's called an astronomical unit. And all they did was they measured from the Earth to the sun. We left it in either kilometers or miles. I want you to know both. And by know, I mean in your notes. And this is called 1, right? This is it's a new measuring system. This is called 1. What is it? 1 astronomical unit. In miles, you can write this down. In miles, it's 93 million miles. That's on average the distance between the Earth and the sun. In kilometers, it's 150 million. So what's an astronomical unit? Well, if you're 1 astronomical unit away, that doesn't mean from the sun necessarily. It's just the scale that we use. So we could say, how far are you from Mars in astronomical units, or how far are you away from us to the Kuiper belt or something like that. Another word you haven't heard of. And we can measure that in what's called astronomical units. But how far is 1 astronomical unit? It's the distance, the average distance between the Earth and the sun, which is approximately 93 million miles or 150 million kilometers. Which works great as long as you're measuring things within our solar system. Right? By the way, that's the Earth to the sun. Generally speaking, when you first learn about the solar system, they draw these nice little circles that are kind of close together. It's nowhere. If you look at that poster in the back of the room, all the planets are lined up, and it looks like, wow, we're kind of close. We are nothing like that. That's the only thing that's wrong with the poster, is that the distance, this is the size of the dots on that poster right here are the actual size of the planet relative to the sun. So we are called the 3rd rock from the sun because we're a rocky planet. Well, here's the Earth right here, and you can notice its general size in relationship to all the other planets. But what's not shown here is the distance from these planets to the sun. It looks like they're all really close, and they are not close at all. This picture right here on the board right here that you see is the actual distances between, these are called the inner planets, from Mars inward. So the first 4 planets, and that does represent the right distances. So roughly speaking, you can see that there's a pretty big space between Earth and Mars, but between Mercury, Venus, and Earth, roughly, we have the same type of radii. All right, AU or astronomical units are abbreviated AU, as you would think. The but here is that as soon as you start measuring things outside of our solar system, anybody know? What's the problem with having a picture of the Milky Way?
We're in the Milky Way.
We live in the Milky Way. So it's like we live in Colorado, take a picture of Colorado. Well, I can take a picture of the tree over there that's in Colorado, but you want a picture of Colorado, you have to
leave Colorado.
You got to be above Colorado, away from it, in order to take a picture of it. So that's why we don't have pictures of the entire Milky Way. This is anybody? It's a pretty. Turn the lights down, please. This is a really good photo too. This is not the nearest galaxy. This is a galaxy, by the way. Not the nearest galaxy, but if you talk about it in terms of large galaxy, this is the nearest. This is the one that's going to kill us, by the way. You've probably heard that there's a galaxy on collision course with us right now, right? Right now, there's a galaxy heading toward us, and we're going to smash together, relatively speaking. And by smash together, it just means we're going to kind of occupy the same space. There is so much space inside of a galaxy or even a solar system. We're not literally talking about crashing into each other, but we're talking about they come together type thing. This is the Andromeda galaxy right here.
What
And
happens when the two suns will collide?
well, we're talking galaxy now. We're not talking about solar systems, right? So we're talking galaxy. The Andromeda galaxy and the Milky Way as well is made up of hundreds of billions of stars, right? We have one star, our star, the sun, right? But what you're seeing here, you're seeing no individual stars here. You're seeing the light coming from billions of stars.
Oh,
And this is, and you can see this with even a moderate telescope on the Andromeda galaxy. You've probably heard it as well too. The nearest galaxy is the Canis Major, the big dog, Canis Major, right? The Canis Major galaxy. And it's actually a dwarf galaxy. It only has about, I want to say about 1 billion stars, something like that. So it's very small. But most time you look, what's the nearest galaxy? They're talking about large galaxies, the Andromeda. And we are on a collision course with it. It will happen in, I want to say, 7 billion years. I think that's right. 7 billion years. We're going to collide. But guess what's going to happen in 5 billion years? Most likely.
sun go boom.
Our sun, well, our sun won't go boom, but our sun is going to expand outside of the orbit of, I mean, it's going to expand like it ate too much, right? It's going to expand outside the orbit of Mars. That's a problem for the Earth because we're inside the orbit of Mars. So the Earth will die long before our solar system or our sun changes form, and long before the Andromeda galaxy collapse. You know, the three main life-ending, species-ending things that will happen is they always talk about Yellowstone erupting, right? Yellowstone is a super large, they got a special name for it, super massive volcano. And if it erupts, we're all dead. That'll probably kill us first. And then the second one is our sun is going to die, and before it dies, it expands. And then the last thing is we're going to collide with Andromeda. So those are the ones, and luckily for all of us, those are probably all outside of our lifetimes.
And then I'm not wrong.
Or I should say, not probably. Yellowstone is probably the only one that if there was something to worry about that one.
And then, correct me if I'm wrong, isn't all these galaxies also orbiting a black hole?
Well, we're a little bit off topic here. The middle of galaxies is a black hole. In the middle of large galaxies is what's called a supermassive black hole as well too. So the middle of the Milky Way is a black hole. Yeah. We will learn about the life cycle of stars. Some stars turn into black holes. Other stars turn into dwarfs, and ours is going to turn into a dwarf. We have what's called a yellow dwarf sun right now. We just have an average size star. And when it dies, it basically expands and then it collapses and then it cools down. All right, a little bit off topic. Okay, so the Andromeda galaxy, why do we measure things in AU? Well, if we start measuring the Andromeda, so its diameter, that says about 14 billion AUs. So, and remember, 1 AU is 93 million miles or 150 million kilometers. So take that number right there and multiply, what do you want in miles or kilometers? Miles, multiply that by 93 million, and that's how wide the Andromeda galaxy is. By the way, how far it is away from us, let's see, that's once again in billions, so 160 billion AU away from us. It's pretty far, right? When we start talking about space exploration, we'll talk about how long it would take us to reach these places with known technology. It's a pretty sad story. All right. So when we get to very, 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 very large, we're talking about sizes of galaxy. We start measuring things in light years. Light year, as the name implies, is the length of time measured in distances, right? That it would take, I said that really poorly. A light year is the distance that light will travel in a year. There, I said it correctly there. So a light year is the distance that light travels in 1 year. So take your flashlight, turn it on. The light leaves your flashlight and goes in a direction like this laser beam I have in my hand right now. If I turn this on against the wall, it looks like it's turning on instantaneously. It's not, right? Wait a year, and where that green dot now appears, that's what's called a light year, that distance, right? 1 light year is about 6 trillion miles. 6 trillion miles. We're doing a little bit of rounding there. So how long does it take for this light? I'm flashing my laser pointer here to get to the wall. Well, it goes one meter is about 3 feet. So about this long it takes 3 billionths, not nanosecond, sorry, about 3 billionths of a second. It'll go 1 meter. Which seems like it's awfully fast. I mean, we can't see it, like the difference between me pressing the button, the light turning on. It seems to us to be instantaneous. But we can very easily see that the ramifications of this. We start talking about even small astronomical distances, like the distance between us and the moon, the distance between us and say Mars, where we have right now, I forget, it's the end of the month. There's going to be something landing on the moon, and right now we have a couple vehicles driving on Mars right now. So we want to communicate to those things. It takes like 1.3 seconds to get to the moon from the Earth. So for instance, when we look up in the sky and we see, hey, look, it's the moon. That is light that just bounced off the moon, and 1.3 seconds it hits your eye.
Oh, cool.
When you listen to astronauts, when we land on the moon, when they were talking, there was a 1.3 second delay between when they would talk and you would hear it. So they would start talking. Oh, now I hear it, because it would take 1.3 seconds.
Similar to phone calls.
Yeah, we talk about to the sun takes 8 minutes. So not that the sun's going to explode right now, nor will it, right? But if the sun were to explode, we wouldn't know about it for 8 minutes and 20 seconds. Because light's fast, it just isn't that fast, right? Light's very fast, right? Mars is about 6 minutes, right? We talk to the spacecraft on Mars, it takes about 6 minutes for our radio. Remember, radio signals is part of the electromagnetic spectrum, so light and radio waves travel at the same speed. So it's a long ways, and a long time when we start talking about that. So if we want to talk about Pluto, which is way far out there, which we've had spacecraft visit. I don't know what it is for Pluto. We can calculate that though. It's a while. So here are our 4 distances you need to be familiar with: imperial, miles, SI, meters, kilometers, AU, 93 million miles, 150 million kilometers, and light years. Yep. Okay. All right. You've already copied down this definition before. The universe, remember, it's everything. Space, time, matter, and energy. And the universe is very large, very large. It isn't necessarily, for some people, this is a scary concept. This is usually the thing that you're laying in bed awake at night and you start thinking about this kind of stuff. And it can be, for some, a scary thought. You think about if you're just standing out like the activity I ask you to do, stand out in the dark and look at the sky. You can basically see from left to right about a football field, right? That would be 0.01 or 100th of a kilometer. Kilometer is about 1,000 meters, or I shouldn't say about, it is 1,000 meters. All the pictures in the book have this little squiggly thing on the bottom. I will describe what that is in chapter 3. Maybe you can figure it out yourself. But when you look at, by the way, this was the Hale-Bopp comet. This was in my lifetime. It was in the 90s, and it was, of the things I've ever seen in the night sky, the most amazing thing. And it was that big when you saw it too. I mean, it was the size of your hand in the sky, and it was magnificent. And in your lifetime, there'll be comets as well too. Comets are there right now. Some of them, most of them we can't see, but the really big ones, you'll probably see a couple times in your lifetime. We talk about the Earth itself. If we're talking about a diameter, that's 15,000 kilometers is the diameter of the Earth. If we expand out to the solar system, we can't use kilometers. There's too many zeros. So we start talking about astronomical units. If you look at the lower right here, it says that distance right here, about the distance of my forefinger, is 10 AU. Remember, that's going to be multiplied by 1 miles, 93 million miles. So 93 million miles, about 100 million miles, right? Every time I put my finger in here, I'm going 100 million miles, right? Across. This is not the entire solar system. There's something called the Kuiper belt, not the asteroid belt, but the Kuiper belt. Kuiper belt is a type of asteroid belt. And that's not even the end of the solar system type thing. That's just, this is where Pluto lives, out in the edges of the Kuiper belt. We talk about, once again, this is a galaxy here, the Andromeda galaxy here. We talk about the galaxies. We have to switch our scale now to light years, otherwise you get too many zeros. And the scary part about this is thinking about your relationship to all of this. I mean, we haven't even begun to even approach the end of the universe, right? This is just one of billions upon billions upon billions upon billions of galaxies, right? This is a very famous photograph. They took a telescope and pointed at a supposedly black part of the sky, about the size of a pencil point in the sky. Think of putting a dot in the sky. Supposedly to the naked eye, it's black. And when they look at it, these aren't stars, these are galaxies that you can see. And remember, each one of these, roughly speaking, about 100,000 light years across. 100,000 light years across. And each one of those makes up that. And that's just one little tiny part of the sky. Put the entire sky together, and scientists have done this, it's roughly about 93 billion light years, which is a nice friendly number, right? We like 93. 93 isn't that large of a number. The problem is it's in light years. And it's not 93, it's 93 billion light years. The universe is so large. The scary part is like we're part of the universe. And remember those 3 questions I said about, why do we do astronomy? Well, it answers those big questions. What's it all about? Why am I here? What's going on? And so when you start thinking about the size of the universe, it can become a little overwhelming. So one of the reasons for this class is to try to make the overwhelming a little bit, not underwhelming, but to at least be able to begin to wrap your head around what's going on. All right, the universe is big. You can get lost in the numbers. 93, like once again, sounds like a nice friendly number, but it's not, because it's in billions and it's in light years. Okay. All right. Now I like to tell stories in astronomy, both for the history and for what's really going on. So let me tell you a story. Early humans, right? We're no different from us in terms of lots of things. I mean, same brains, right? The difference between us is maybe we had better clothes, better sanitation, better medicine, but our brains work the same way. So they would be awake at night. A natural inclination was to look up in the sky and witness the beauty of the heavens. Well, they had to do something. We're humans, right? Anything that happens, we want explanation of what's going on. So the early humans, because they lacked the science, they would look at the sky and they would make up stories that explained what they saw. And they literally made up stories. Okay? One thing they saw in the night sky was this thing. We've already seen a picture of it, right? There's a story behind it, right? All this graphical detail that's on this particular slide right here doesn't actually exist. What exists are the individual dots of light that hopefully you had already seen, but we know it was cloudy the last couple of nights. You didn't get to see that stuff. Somebody made this up, right? Somebody actually said, I see a dude with a shield and a club or a spear, right? Depends upon what they saw. This is turned more in the relationship that you see it. As it starts rising at night, it starts in this position and he stands up and then he lays down, okay, as the night goes on. This is a bit exaggerated what you see, but this is general. By the way, we're missing the top star and the bottom. There's another bright star here, another one up here, but this is the picture I got. But you will absolutely, and probably some of you saw, a lot of people that look at that and they say, look, it's the Big Dipper, the Little Dipper right here. This is not. You're looking to the north, right? You're going to see the Big Dipper, but if you're looking to the south, which is where Orion is, this is how you know you're not seeing the Big Dipper. Which is why it was important to, the first thing on your sketch was to figure out what was north, south, east, and west.
Yeah, but meteor shower was in the northwest.
Yeah.
That's all I remember.
This is a bit more on a really good night, what it would look like, right? And this is still a bit, I mean, you're probably not going to see this. This is early in the evening. He's trying to stand straight up, but this is Orion right here. This is Orion. This is his sheath to his sword, and he's standing up and he's got a shield, but I don't know about you, but I certainly don't see that, right? And here's the picture of it right here. All right, quick tangent, right? Many people have looked up and seen things. As you flip through the book and they start showing you pictures of things right there, especially the cool, interesting ones, not just Orion, but other things, you're going to get they're going to be called M something. They're going to say, hey, look at M61 or M10. This is the guy responsible for it. His name was Messier. In the late 1700s, he liked comets, right? And so he would always try to find comets. And when he had a telescope, and when he tried to use his telescope to look at comets, he saw stuff. and he really couldn't explain what he saw, but it was cool stuff. It was colorful. And he was like, "Ooh, look what I found. Look at this stuff." He was one of the first person to say, "Hey, I'm going to give names to these things." And since his name begins with M, this is where the M comes, and these are called catalog names of some of the things. So when he saw this stuff that got in the way of what he was trying to look for, he's trying to look for comets, right? He listed roughly 100. There's some argument about whether he had all 110, but he listed about 110 of these, right? They're called Messier objects. And so once again, as you're flipping through the book and you see M10, M61, there's lots of them, there's 110 of them. Here's all 110 of them right here. And they're really interesting objects, right? And they're called Messier objects. To complicate the picture, there's more than 110 interesting things in the sky. So nowadays, we have a different method of cataloging these cool things that we see in the sky. One of the coolest of all coolest things right here. This is a ball of gas that's being heated, and as it heats up, it gives off light. And it's just beautiful. But there's way more than 110 interesting things in the sky. So nowadays we use what's called the NGC number. So as you're flipping through the book and it says M61 or NGC and a number attached to it, just realizing that's what it is. NGC stands for New General Catalog. There are thousands upon thousands upon thousands of these things. All right, back to our story. Oh, by the way, I said this is a note-taking class. If you're ever in doubt, wait, I didn't write that down. Was I supposed to write that down? You can always ask me, hey, should I have written that down? All right, back to our story. So ancient man, ancient woman would look up at the sky and they would say, hey, that looks like a guy with a shield and a club. Anybody know what this one is?
Apollo.
Yeah, so what's his story?
I know he's the god of sun, music, and medicine.
So what is that showing right there?
He's pulling.
As the story goes, he's riding in a chariot, pulling the sun along with him. This is how ancient civilizations and most civilizations had a story similar to this. Obviously, this is in the Greek and Roman tradition, but their explanation of what the sun was, well, there was this bright thing in the sky, ball of fire that this god was carrying across the sky. No, we know that's not the story, right? The but here is, of course. Today, of course, we know that's not a story, but we like stories as humans. So we've retained some of those stories, not that particular one, although some of you already knew it, so clearly we have retained that story. I'm saying we've retained much of the stories that ancient humans, when they looked at the sky, what they saw. We still call it Orion, even though it's not a dude in the sky, right? Much has changed, but we've kept some of the things that ancient people saw in the sky because they're good stories. Some of the stuff that I tell you in astronomy class is going to change in your lifetimes, right? But some of the cool stories will probably persist simply because they're good stories. I will, throughout the course, I'll try to tell you some of the better stories, right? When we talk about the names of the planets, I'll tell you the stories behind them of why they're named that way. Okay. All right. The rest of the first two chapters does one and only one thing. And it describes how we went from, we knew nothing about what was going on. We made stuff up. And hey, there's a guy, he's pulling the sun. That's the real story. Completely made up. There's not a speck of truth to it. It kind of relates to what they see. Feels hot. Hot comes from fire. Yeah, there's some bits of information there that sort of makes sense. But as soon as we find out there's no oxygen in space, there's no fire up there, right? It couldn't be the story. Clearly, it's not a god carrying the sun.
Yeah, that'd just be stupid.
Well, but I'm saying the story still persists because it's kind of a cool story. But the first two chapters describes how we went from caveman who had little true understanding of the universe to our current, and I'm going to say less knuckle-dragging understanding of the universe. And why I say less is because we don't know the full story. There is way more that we don't know than we do know. Many things we know with certainty, either because we've been there, we take direct observations, or we've proven that someone's hypothesis was true. We have never been to the Andromeda Galaxy, yet we know what it's made up of. Why? Well, that's kind of chapter 3 story. I mean, how do we know something if we haven't been there? It's like looking out and seeing something over there and saying, I know what that is, right? Not because I go there, but because I know something about it. That needs an explanation. That's chapter 3. And it will be, chapter 2 is a historical journey. We're going to talk about it. And I said it before last class, it's kind of a repeat what you learned in sophomore history. But it should be good and entertaining. So it's a historical journey of cluelessness to our current understanding of the universe, less clueless, right? How was this accomplished? How did we get so much knowledge, right? How do we go from this understanding of the sun to, hey, this is an actual picture of the sun, right? Ancient humans had no depiction of what the sun was, yet we haven't been to the sun, right? We've been close to it, but we've never been to the sun. And we got a near perfect explanation of what's going on in the sun. Like we know why it works. By the way, back up 200 years. Let's see, back up 150 years. We did not know what was going on with the sun, yet now we do know. Okay. So how did we go from one extreme to the other? Well, clearly we used our brain and
our eyes.
We'll call that part of the brain as well too, right? The eyes or the brain processes what it receives from the eyes, but we've used our brains and say again, and definitely technology. I mean, we've either physically sent things to those locations or received information, or we gathered information from the light emission from those objects itself, or any other type of radiation coming off of those objects. Okay. All right. The key to all this is the scientific method. We talked about that was the name of this class was. Part of it was the science, measuring units and scientific method. Okay, you've had scientific method class since probably 2nd grade. What's the scientific method? What's the scientific method? It's usually the first week of every science course.
Yeah, it's so.
So what's the scientific method? There's something over there. I don't know what it is. I think it's a bug. Okay, technically it starts with an observation, right?
Yeah.
Or thought, right? And you make a hypothesis. And then what? I think it's a bug.
Then you figure it out.
Well, if it is a bug, then I should be able to walk over there, pick it up, and do some experiment on the bug and confirm that it's a bug, right? If it really is a bug. Oh, wait, it's a piece of dried fruit. It's not a bug, right? I do an experiment, find out it's not a bug, it's a piece of fruit. So what's the next step of the scientific method? Ooh, this is going to be a long class. All right, let's write this down. We did not have the scientific method until about the 17th century, right? The scientific method, although parts of it were used many times, but formally thought of as a process, happened somewhere around the 17th century, so 1600s, right? Coincides with the Renaissance Reformation, right? It's the process of you make an observation, you form a hypothesis. I'll keep the slide for a second. You make a prediction. If that's a bug, it's going to crawl along the wall because bugs move, right? You test that prediction. Hey, I watched that thing there for 16 years and it never moved once. That's not a bug. I believe the longest experiment in history, which is still going on, by the way, is a couple 100 years old right now. Something about it's a piece of matter in it. It's like it's not plastic itself, but it moves at a very slow rate. So they hung it and they're waiting for it to make a drip and drop down. It's been going on for a very long time. We test the prediction and then what's called we iterate. Hey, if it is this, it should do this, right? And then we repeat the process or we change it. Hey, it didn't do this. Well, therefore, it ain't a bug. I got to change my hypothesis and change my prediction. Okay? This is the scientific method right here. And this is why you all have, well, hopefully not. This is why you all have cell phones in your pockets, right? You have a cell phone in your pocket. I mean, you would be killed for this, 300 years ago. I mean, witch, burn the witch type thing. You got a screen, it talks to you. right? I literally can talk into it, it'll talk back to me, right? It'll even answer questions. It seems like, magic. There's a famous expression that says, any good technology seems like magic to anyone, a couple hundred years ago. But the scientific method was able to drag us out of that. Oh, I think it's a guy pulling a burning object, and that's what the sun is. To, well, if that's a case, then you need to make a prediction based upon that. Then the horses have to eat. Well, if the horses have to eat, then there's got to be food. So something like that. Whereas when science got involved, all of a sudden people, maybe it's a fire. Well, if there's a fire, then there has to be oxygen and fuel and heat, and we can identify the heat. We can identify or we can't identify the oxygen. Therefore, well, it isn't that, and they continued on with their predictions of what it should do in case it meets this one particular hypothesis. Are we okay on the slide? Scientific method. All right, so let's start our journey. We joy and appreciate these stories. I mean, there are good stories, right? We understand the myths that came before the science, right? Anybody? Anybody? Got horns? Say again? That's maybe what is in Spanish. We call it. Oh, this is Taurus. Taurus the bull.
Oh.
Right?
Oh.
We rely on the work of the people that came before us, the astronomers. By the way, interesting fact, you know more about astronomy, even though you haven't taken the course, than anyone that was alive in the 1400s. You know more about it, right? Wait another 600 years and they'll, high school students will know way more than you know, right? At the end of this course, right? Your knowledge will be thought of as child's play, right? Even though all of these great, including Einstein, we know more than what Einstein knew, I should say. Why? Because the science has progressed. We know more things now that even he knew. I'm not going to say we're smarter than any one of these, and we're going to learn each one of these guys. But as science progresses, our knowledge only increases. Okay. So it's going to be a journey from caveman to spaceman for the next 2 chapters. Yay for us. Okay. All right. What time we get out of here? Is it 55? Okay. So we're going to get started on the next one. And this is typically how it works, is that we will never, or usually never, end right on a bell. First time I taught this, I tried to do that, and it just didn't ever happen. Okay. All right. Here's our next thing. It's just pages 10 through 12. So 3 pages, a whole lesson on 3 pages. And it's section 1.3. Oh. What's this green thing say right here? I'm not 100% sure I'm sharing this with Cammy right now. Does the red thing say sharing? Stop share?
That says stop sharing, I think.
Stop share. There we go. Now I need to find my mouse. Share screen. I want to share this one right here. Share. Okay. All right, ready? Yeah. Go. This is going to be an obvious view, obvious in quotations. All right, we're going to learn these words right here. All of these. How many of these do you understand right now? Cosmos, you've heard the word. Anybody know? Nobody? Constellations. We're going to talk about these constellations. What are these?
Because they're important to know.
Anybody know? Ursa Major, the Crux, and Cassiopeia.
They sound like they're important for
Okay.
humans.
Astrology, you've heard about Polaris?
heard it, you know what I mean?
Celestial sphere.
Isn't Polaris, part of the reasoning for true north?
Very true. All right. All right, so the keys to passage from it, I need to remind you is to take good notes. Make sure they're organized. They're just not haphazardly written down, and look at each slide and identify and write down the important parts, i.e. the parts on the quiz. Once again, you can always ask me, should I have written that part down? To make sure you understand the basic gist of every slide I talk about. All right. And then I would always recommend that you review those, whatever notes you take every single day in essay, if it's just reading it across. All right, I've said this, I've said that, I've said that. Where do we leave off? Last class we talked about, last class was 2 minutes ago. We talked about those things right there in general. We talked about the universe. We talked about the universe made up of galaxies, solar systems. Didn't necessarily say this, but inside the solar systems, you have a star and you have planets. That's what makes a solar system. And astronomy means something about looking up and explaining what you see, right? So let's look up. First new word, cosmos. The universe, which is everything, as a complex and orderly system. The universe just says everything. But there's an order to things. It's just not, there's something going on up there, right? There is almost a mechanical movement to things up there. And if you apply order to this universe, you get this idea of cosmos, right? It's the opposite of chaos. Now, people tend to use the word universe and cosmos synonymously. But just remember, if you're using cosmos, you're saying not only is it stuff, there's some pattern going on up there. Hey, why do all the planets go around the sun in the same direction? Why don't they go in opposite directions? Right? There's some order there, and a specific order that needs some explaining. That won't be to chapter, I don't know, 4 or 5. Trivia. Greek cosmos means order. Cool. Yes. Okay. So recall that the impact of the scientific method, right? Greeks, Parthenon, Acropolis, right? The Greeks. They had this great story about some god that carries the sun in a chariot and goes across the sky, and that's why the sun moves, right? Complete and total baloney, right? Everybody can look at the sky and make observations. You're doing it. I'm asking you to do that every single week, right? But we've also sent things to places. I mean, this is Mars, by the way, and this is not today. I didn't take this today, but we have multiple cars that are driving. Somebody's driving it, right? But they're driving it from the Earth. They put on virtual reality goggles and they drive the car around.
Is it
Right?
like a 6-minute delay though?
There's a 6-minute delay. So guess what? What they have to do is they tell the car where they want it to go, right? And then the car itself has software that avoids obstacles. So it will say, okay, I know where you want me to drive. I'll drive there. If I encounter a problem, I'll stop and call back and say, hey, what do you want me to do? Okay. They practice driving it and they're like, oh, this looks like a pretty good route. And then they can do it. All right. We begin our study of the cosmos by looking at the sky, right? The appearance of the sky is basically no different than what ancient caveman, right? Even though caveman was hundreds of thousands of years ago, the sky that they see is, generally speaking, exactly the same sky that we see. There are some differences, but not vast differences. They saw Orion. They saw the Big Dipper. They saw the North Star, right? They saw the same, they saw the sun, obviously. They saw the planets. They see the same thing that we see. The only difference is that we have more knowledge of what we're seeing that they did, right? Our interpretation of what we see is very different from theirs. Remember, they had all these great stories, but we know that those aren't true. It's not a guy pulling the sun. We know the sun is a big ball of hydrogen and helium, right? Nuclear fusion going on. All right. So let's consider observing. Now, I don't want to insult your intelligence, right? But when it's daytime, we are facing the sun. And when it's nighttime, we are not facing the sun, right? So even though there are stars in the sky right now, the reason why we can't see them is because it's like looking into a flashlight. You see the flashlight very well, but you don't see that Chloe is right there. If I'm shining a flashlight in my face, she's still there. So it's not that the stars disappear, they're still there. Further, you're smart enough to know that one of the reasons why we change from night to day, from day to night, is because the Earth is spinning along its axis. We have a whole chapter on the Earth, and we'll talk about, hopefully you remember, it's 23.5 degrees tilt to it. Roughly speaking, this is a good one to know. Most people don't know this, right? Roughly, during the night, you can see about 3,000 things in the sky. Roughly. Like, when you do your sketches, I don't want you to be sketching 3,000 objects.
Wow.
And it also depends upon how well you can see. Like, even with my glasses, I don't see 3,000 objects. But there's, on a good dark sky, there's 3,000. So you think about that and what I just said about the sun, how many things can we actually see in the night sky? If on any given night you can see 3,000, in total, how many things could you possibly see? Not 3,000.
You can still see the moon and the sun.
No, you're not going to count all 3,000. Hey, if you can see 3,000 objects this way, there's 3,000 objects that way as well, too. So in general,
6,000.
of the possible observable things, we can see roughly about 6,000. You're like, well, yeah, but you just said you can only see 3,000. Yes, because it's dark on one side, you can see the stars, you can't see the stars on the other side. But the Earth moves around the sun. So at various times, you get to see 3,000 objects. At other times, there's another 3,000 objects you can't see, right? So without the sun, roughly 6,000 different points of light are visible to the Earth. Notice I didn't say there's 6,000 stars, because not everything is a star. If you listened to me before, I said that galaxies are made of hundreds of billions of stars. So what the heck are you seeing? We live inside of the Milky Way. You're clearly not seeing all the stars of just our galaxy. There's 100 billion of them, hundreds of billions, right? So what are you seeing? You're seeing things, stars and some other things as well, too. With the naked eye, it's very hard to see galaxies. We're generally not with a telescope, we can absolutely see some galaxies. But with the naked eye, most of what you're seeing are planets, stars inside of our galaxy. And maybe if you're lucky, there's just a handful of other things that you can see. All right. The lights that we see with our eyes. Certainly we see the stars of our galaxy. Not all of them. There's hundreds of billions of them. We see the close ones. The glow that you see that we say is the Milky Way is the collection of light of those hundreds of billions of stars. Definitely can see, not all, but some of the planets. Let's see, we can see, if we're really, really good, we can see Mercury, we can see Venus. Obviously, we can't see the Earth. We can see Mars, we can see Jupiter and Saturn, and that's it. With your naked eye, you cannot see Uranus, Neptune. You certainly can't see, Pluto's not a planet, but you certainly can't see Pluto. If you were alive roughly 300 years ago, you didn't even know some of that stuff existed. You certainly didn't know Pluto. Pluto was discovered in the 20th century, by the way. Last one discovered. I shouldn't even say it like that, because we've discovered other type objects like that are as large as Pluto. We'll study them this year, that are in our solar system as well, too. Certainly can see the moon. Few galaxies, we're talking a handful, and you got to have good eyes. I mean, really good eyes. A galaxy, or me, the galaxies will appear as a smudge, like a really fuzzy white object in the sky. I've never seen a I've seen plenty in the telescope, but I can't see any of the galaxies with your naked eye. And lastly, there's other things that you will see occasionally. We talked about comets. If an asteroid comes close to us, we can see that. We certainly see meteors streaking across. Those are your shooting stars. And you can see satellites crossing as well, too. And we'll stop right there. Pick it up tomorrow. Remember I said you have until Thursday for those 2 sketches. So Thursday in class, I'll collect the books. I'll grade them back and give them back to you on Friday with a new assignment.
Wednesday.
Yep.